Hello everyone, I'm Anthony Johnson. I'm here to show you our FlexSim's new agent module, which we're releasing as a beta. Uh, we've had a lot of requests from our users, given the current COVID situation, to allow them to detect and do simulations and statistical collection on things like social distancing, um, spreading of a contagion, etc. And so we have created this module so that hopefully those problems can be solved a little bit more easily in FlexSim. Let me show you the interface of how you go about it. So if I were to have an object or one or more objects in my model, I could select them or right click on one of them, and I get an agent systems submenu or right click menu, and I can add a new agent system. Right now there's kind of two types of agent systems. One is a new proximity detection system, and the other one is a social force system. So if I add one of them, then I get this window up, which is an agent system properties. You can also see that agent system in your toolbox. You can also add an agent system in through the toolbox. Okay. So what is an agent system? First, it is a set of agents. So if I go to this agents tab, I can see all of the agents that are members of this system. Second, it is a set of behaviors. So each agent can have one or more behaviors active. You can activate and deactivate certain behaviors during the simulation module or during the simulation of the model. Each behavior has an update interval. This is kind of like a tick where it moves forward in time, and then it'll update all of its agents based upon certain rules. Basically, there's two types of behaviors. There is a proximity detection behavior and a social force behavior. I'll talk about social force behavior later. Proximity detection is essentially that. It is detecting proximity between different agents. So it'll, on its update interval, it'll go through each of the agents, and then it'll find neighbors who are within proximity of that agent. And you specify a proximity radius. When it finds one, then it'll enter into proximity with that agent, and then it'll fire this event, and then for every neighbor that a given agent is in proximity with, it will fire the on in proximity event on each update interval. Then when it leaves proximity, when it exits proximity with a given neighbor, then it'll fire the on exit proximity event. So that's essentially the proximity behavior. I can show you basically a basic system that has this set up. The idea of this was just to test everything out to make sure that everything is working. But it shows, so in this case, what I'm essentially doing is I'm just trying to color things based upon proximity. So if I run this model, the idea is I have a process flow that's essentially starting up and telling everybody to move to walk to random points in the model. And then when they come into proximity with each other, I just want to turn them red. And when they leave proximity with each other, I turn them back to green. Okay. If I look at my agent system here, I have an agent system called proximity. It has an update interval of 0.2 seconds, a proximity radius of 0.5 meters, and then just two triggers, which is on entered proximity, I color them red. On exit proximity, if I have nobody else in proximity, then I color them green. And so this is the idea of this is, in a lot of cases, this may be enough for what you want to simulate. If you just want to kind of detect who is in my proximity, and based upon that, just collect some data, or you may make decisions or update certain state or values, some risk of a contagion based upon who is in proximity with you. Um, Let me kind of talk a little bit about the secret sauce of the agent system. You can see here, um, it draws, I've checked this box in the general tab, which is show agent state info, and this kind of shows various things. One of the things that it'll draw is a kind of a bounding box around that operator. The second one, and that's just based upon, or that's just kind of that's the neighbor's bounding box or the agent's bounding box. You also have a circle. This is based upon the behavior that I've activated. So in this case, I have a 0.5 meter radius. If I were to say 1 meter, then it would increase those bounding boxes or those circles. Now, the way that it detects proximity is when the circle of a given agent collides with or intersects a bounding box of a neighbor. The reason I do a circle with the bounding box is so that I can also have walls be kind of detected. So a wall would have a pretty long bounding box. I could detect the wall within my radius without having to do a radius thing on the wall itself. It could be the bounding box of the wall. Um, the other thing is the kind of the secret sauce of the way that it works is it uses what's called a bounding volume hierarchy. I can show this in the 3D view. What it's doing is it's essentially partitioning the space into a hierarchical set of bounding volumes. The advantage of doing it this way is if I want to see the closest neighbors to this agent, for example, I can search the bounding volume and I can much more quickly hone in on those neighbors that are nearest to this agent. This is significantly faster than if I were to just go through every neighbor and detect proximity with every other neighbor through a brute force mechanism. So that's kind of I guess, the unifying principle between all agent systems or in FlexSim is it manages this bounding volume hierarchy so that it can detect where neighbors are much more quickly.
Here's another example of using a proximity detection system. This is specifically for an AGV system. One of our German distributor requested a specific type of behavior that was not part of the standard accumulation behavior in AGVs. What he wanted was kind of a two-speed system where if AGVs don't have anybody near them, then they will go their standard speed. And then if somebody comes within kind of a small proximity, then they will decrease their speed down to a slow speed. Then if they get really close, then they'll actually stop. So it's kind of two speeds and then stop. Um, you can simulate this with with an agent system using the proximity detection behavior. So I'm going to double click on this. I guess first let me go to the agent AGV network. So I have set up two different speed modes. I use this. This is the load types. I use the load types, and I use two of them. There's a fast speed and then a slow speed. And then I use a label on the AGV. So when I want to go into slow speed, when I want it to go slow speed, I will set a label. And then in the initialized travel, I will say if the AGV has a label called slow and it's 1, then I want it to be the second load type, which is this one. Otherwise, I want it to be the first load type. And for the first load type, you have a max speed of 1, and for the slow speed, you have a max speed of 0.5. So once I've set that up, then I go into my AGV system, or my agent system, and I specify two different phases. I call them phases for proximity detection. I have a broad phase proximity detection and then a narrow phase. The broad phase has a smaller, or I guess a larger update interval, so it's not updating as frequently, but it has a larger proximity radius. Okay, when I come into proximity under that broad phase, then first of all I activate narrow phase, which is this uh, second behavior. But I also do some additional things. First of all, I do some math to make sure, hey, he needs to be in front of me. I don't want to go into narrow phase if the guy is behind me. So I do some geometry math to say, hey, if he's not in front of me, then don't even enter. When I return 1 out of this enter proximity trigger, what that means is essentially cancel. Do not enter proximity. Assume that you're not in proximity. If I get past that point and my math works, meaning he is in front of me, then I set my object to slow. I change him to his color to yellow. I activate the narrow phase behavior. And then what I do is I just give him a task sequence that preempts him and does nothing. What that will do is it'll break him off of his current travel task and have him do nothing, and then he'll just start up the original task that the task that he was just doing. And so what that means is he will restart his task, he will reevaluate that initialized travel, and he'll figure out which phase he's in by the fact that I have set his which load type he's in. By the fact that I've set his slow label, then he'll go into the slow load type. Once I've activated narrow phase, the narrow phase has a higher interval, or a more frequent update interval, and a smaller proximity radius. When I come into this one, then I want to stop the AGV. So in that case, again, I do some math, make sure that he's in front of me, but then I change him to red, and I essentially preempt him to say stop. Once he exits that phase, then I free him up, which is essentially I call free operators on that object. Once I leave broad phase, then I can then deactivate narrow phase, and then I set his slow label to 0, and then I do the same little trick where I preempt him so that he restarts his travel task, and that will cause him to go back into the faster load type with the faster speeds. So if I reset and run, you should be able to see these guys start up. Again, there's some checking. Currently he's in proximity, but he's behind him, and so I don't apply that proximity to him. But when he comes around and comes behind the other task executor, then he will detect, hey, you're in front of me, and go into his slow phase. And you'll notice now he's doing a lot more updates, a lot more frequent updates. And then when he comes into even that smaller proximity, then he will stop. So this is just another application of how you might use this agent-based proximity detection behavior to customize the logic of your model. Now for the second type of agent behavior, which is the social force behavior. With social force modeling, the idea is that your agents are kind of pushed around based upon different forces. Those forces may be based upon the state of the agent, or they may be based upon proximity to neighbors around the agent. One classic computer science example of this is what is called Boids, which kind of simulates flocking behavior, where members of a flock of birds kind of they are attracted to the flock, so they want to stay together, but they don't want to get too close to each other. They also want to go in the direction of the flock. And so you can simulate this by applying various forces to each of the agents. Let me just show you this simulation as it goes, and you can see they're kind of moving around, but they're also affected by those around them and kind of move with the flock. So this is basically a set of social forces on each agent. I have a cohesive force, and I'll talk in more detail about each of these things later on, but I basically have a cohesive force, which is the agent is attracted to the center of mass of his local neighbors. I have an alignment force, which is the agent is attracted to the direction. So the agent wants to go in the same direction as the direction that his neighbors are going. I have a custom force. In this case, I've just defined it to say I want to keep them in the center of the model so that they don't go off into the middle of nowhere. So I add a custom force to kind of say, if you're too far to the right, then I want to push you back to the left. If you're too far to the left, I want to push you back to the right, etc. I have a repulsive force, meaning I don't want to get too close to my neighbors. So if I get too close, then I'm going to steer away from them. I also have a random force, so that creates some randomness in the way that they interact with each other. And I have a momentum force, which is given the current direction that I'm going, I want to continue to push myself in the same direction. So that's the momentum force. But when you combine all of these forces together, you get kind of this emergent behavior that's kind of interesting to watch. Now, our current set of customers may not be as interested in this type of simulation, but it does very easily translate into things like crowd behavior, which I will show later on. This is another type of agent system that uses social forces. In this case, we build on top of the AStar network. So again, let me actually just show it running. Again, each of the agents are affected by forces, but one of the forces that they are affected by is an AStar path. And so the idea is that when an agent gets a task, he will have a path, an AStar path that he wants to go along. And so all other things being equal, he will follow that path. But as other agents come into contact with him, that agent will be affected by forces based upon those neighbors. Okay, so if I look at the AStar system, here again I have similar forces to the last model. I have a repulsive force, meaning I am repulsed by my neighbors. I don't want to come too close to my neighbors. I also have some additional forces, which is a transverse force. This is a force where if there's a guy in front of me and he is coming toward me, then I want to move to the right. So kind of like a right-hand rule, we drive on the right side of the road. If there's a guy coming toward me, I'm going to move to the right so that he will pass on my left, and he will move to the right so that we can pass each other. That's the transverse force. The main thing here that's driving it, though, is this AStar path force. And I'll talk about this later, all of the different parameters of that. But again, the idea is once you have a travel task, the agent system will communicate with the AStar network, and the AStar network will build a path. And then that path becomes a guide for the agent, such that it will be attracted to travel along that path. Here's another model that simulates the evacuation behavior of various agents from a room. And I'm comparing how long does it take to just escape, or at least to evacuate a simple room, and then how long does it take to evacuate a room where there's a little bit of barrier in front of the exit. So I reset and run, it'll create a bunch of agents, and then it'll just tell them, hey, leave the room. And then they will again be affected. It uses the AStar path system, so it'll build a path for them and they will try to go along their path, but they'll also be affected by their neighbor agents such that they will try to avoid their neighbor agents. This is another simulation model that simulates, I guess, the behavior of people walking through a hallway. So if I reset and run, it creates a bunch of agents and then just sends them through the hallway in different directions. It's just kind of interesting to see how they kind of crowd near the entrance to the hallway. Once they are in the hallway, they actually move along pretty quickly, but getting into the hallway can be somewhat slow. At this point, I want to go through and show you each of the different social forces that you can apply to a social force behavior. So I'm going to delete all of these forces and just start and show you each one individually, and then we'll go through each parameter that you can set and what that means. So for forces, you have neighbor-based forces, you have self-based forces, goal-based forces, and then you have a custom force and a random force. So let's start with neighbor-based. First, you have an attractive force. So this is, I am attracted to my neighbors. For each force, and it kind of shows you that an equation, this is, it will sum up for each neighbor, it will sum up the force, which is the normalized vector directed at the agent. For example, from, or in other words, from the agent center to the neighbor center. So it's directed at the neighbor, and then it multiplies that by the distance, the magnitude of the difference vector, which is the distance between the agent center and the neighbor center. Then it raises that distance to some factor that you can specify. So generally this is going to be a negative value. So I raise the distance factor to a negative value, meaning as I get further away from a neighbor, I want the force to be smaller. And as I get closer, I want the force to be larger. Then you take that whole thing and you multiply it by some scaling factor. Once you've defined the force for a specific neighbor, then you sum all of those together, and that becomes your total attractive force to all of your neighbors. You specify a max distance, which is I am only going to apply this force for neighbors that are within 5 meters of me. You also have a set of active rules that you can apply. This is where you can kind of filter or define when is this attractive force applied. If I click the add button, you can see again you have self-based and you have neighbor-based active rules. For self-based, you can say I only want to apply this force when I am traveling. So, or you can say I only want to apply this force when I am idle. And when you click on it, you can then see it in the field, and then you can, if you want to remove it, you can click the X and it'll remove it. So when traveling, when idle, you also can specify it based upon a label value, which is I only want to apply this force when my agent has a certain label value. So I can say, agent, I can say type. If the type is 2, then I have this attractive force. You can then click on it and get that pop-up and define the values again just by clicking on it. And again, you can click the X to remove that. So those are the self-based active rules. You could also have neighbor-based active rules, which is I only want to apply this attractive force based upon certain neighbors. I can say I only want to apply this for neighbors with a certain behavior, or no behavior at all. The default is no behavior. What that means is I only want to apply this to neighbors that have no behavior activated. In this case, in general, what that means is it will apply it to, and I'll talk about this later, it will apply it to barriers in the AStar system. So you can specify, you can set up your AStar system so that the barriers like dividers actually become static agents. So a static agent is an agent that the system is aware of, but that does not have any behaviors activated. You would use this in the case of a repulsive force, meaning I am repulsed away from walls. Uh, you probably wouldn't use an attractive force, but you can apply that to neighbors with no active behavior. You click on it. You can also say, specific behaviors. If I have multiple social force behaviors in here, I can say I only want to look at neighbors, apply this force to neighbors with that specific behavior. Okay. So that's the social force, the behavior based. The other ones are neighbors with matching label value. So I can specify a certain label value, so like type. And then what that means is I will only apply this force for neighbors whose type label matches my type label. Okay, so you can say matching labels, or you can specify specific label values for neighbors. So I can say if the neighbor's type label is equal to 5, then I can apply this attractive force to those neighbors. So those are the different type of activation rules or active rules that you can apply. So that's the attractive force. You also have this per neighbor magnitude. If you uncheck the box, then it changes around the equation. So what it does, if it's not a per neighbor magnitude, is it will sum up each of the individual magnitudes of the forces, and then it will normalize that. Now, unfortunately, you can't see this, but it's a little hat, which kind of indicates normalization. So it'll normalize the summation vector, and then it'll multiply that by some scale factor that you can define. So what that means is, if you uncheck this box, what it essentially means is I want to define what my total force is, no matter how many neighbors I have. I just want to say it's attracted to the center of mass of my neighbors, and I want that force to have this magnitude, no matter how many neighbors I am. Whereas if you check the box, it'll essentially take each individual force and it'll just sum them all up, meaning if you have more neighbors in your vicinity, then that attractive force will be higher. If you have fewer, then it'll be lower. When I uncheck the box, this essentially becomes what we call a cohesive force, and that is one of the options in the neighbor-based menu. A cohesive force is essentially an attractive force where the per neighbor magnitude is unchecked. The cohesive force is you are attracted to the center of mass of your neighbors. The other neighbor-based force, another neighbor-based force is the repulsive force. So the repulsive force is like an attractive force, except it is applied in the opposite direction. So it's applied away from the neighbor. I am pushed away from the neighbor. And you specify a scale factor, and you can also apply an exponent for the distance from that neighbor. And you have the per neighbor magnitude checkbox. The one thing that I additionally have for a repulsive force is I have a hard limit, which is no matter what, I do not want to get closer than 1 meter to that agent. So it'll apply the force for everybody within the max distance, so 5 meters. It'll apply that force, but it's also saying I cannot come within 1 meter of my neighbor. If I get 1 meter to my neighbor, then it'll kind of set a hard point where it can't go past that point. And you have active rules just like the other force. You also have a neighbor-based force, which is a transverse force. I talked about this a little bit earlier,
which is if there are neighbors who are in front of me and they are coming toward me, then I want to move to the right. So I can, if I'm right-hand rule, meaning if I'm in America or other nations that drive on the right side of the road, then I would have a positive value here. If I'm like in England or some British nation, then I would apply a negative value here, meaning I'd like to go on the left side of the road. So what this essentially means is, yeah, if there's a guy coming toward me, then I am going to move transverse to my direction to him. Okay, and again, you have a scale factor and an exponent that you can apply. Here you also have a field of view, which is I'm only going to look at neighbors that are within some field of view in front of me, within 30 degrees field of view in front of me. And you also have a travel direction threshold, which is I only look at neighbors who are actually traveling opposite to the direction of me. So if the neighbors are going in the same direction as me, then I don't care about them. Only if they're traveling towards me. So the difference in angle between their travel direction and my travel direction needs to be at least 120 degrees. Otherwise, I won't apply this force. Again, you have a max distance and a set of active rules. So those are, oh, I forgot, there's also an alignment force for a neighbor-based force, which is I want to travel in the same direction as my neighbors. The alignment force, again, it applies this force based upon in the direction of the velocity of my neighbor. And again, you have a distance factor, an exponent where you can multiply, you can base it upon the distance. So as things get further away, the force is smaller. As things come closer together, the force is larger based upon that exponent. And again, you have a max distance and a set of active rules where you can apply it. So those are the neighbor forces. Next, there are self-based forces. So there's two primary self-based forces, a friction force and a momentum force. The friction force is applied in the opposite direction to your current speed. Generally, if you don't have a friction force and you have no other forces applied to the object, then and he is going a certain speed, then he will continue in that speed. So generally, it's a good idea to have some friction force so that if there's no other forces applied to him, he'll come to a stop. You have a static friction element and a kinetic friction element. The static friction element is applied when the agent has no velocity, so he is currently stopped. And it is generally higher. This is kind of a physics thing where you have a static coefficient of friction and a kinetic coefficient of friction. So if he is stopped, he generally doesn't want to start moving. And so it will be higher, and this becomes a threshold, meaning if he is stopped, then all of the other forces that are trying to get to move him must add up to at least a total value of 0.5 in order to get him to start moving. Once he is moving, then it'll apply the kinetic force, in which case you can apply a certain factor, as well as you can scale it based upon his current velocity. By default, the exponent here is 0, meaning I don't care what the velocity is. No matter what, the friction is going to be 0.1. But if I say, something like a positive value, then that means as the velocity gets higher, my kinetic friction will also increase, so that I will have more of a tendency to slow down as my velocity gets higher. The other self-based force is a momentum force. So the momentum force is similar to the friction force, except it is applied in the direction of your velocity, meaning I want to push myself to go faster along whatever vector I am currently going. And so you don't have a static friction. It's just a momentum force that says wherever I'm going right now, I want to continue in that direction. So those are the self-based forces. You have a goal-based force. So the goal-based forces, there's two of them. One is your travel destination force. This is if I have again, I guess when you apply a goal-based force, then the agent system becomes a navigator. It will become the navigator of the object such that when the object gets a travel task, it will notify the agent system, hey, I need to get to this location. And then when you have a goal, it'll set the agent to essentially have a goal, and then any goal-based forces will be applied. You generally do either or, not both. But the goal-based force, this would be a straight line force. So you are just attracted directly toward your final goal. And you specify the force, again, a scale factor, and then you can raise the distance from your goal to some factor. So if I have this be a positive value, then that means if I'm further away from my goal, then this force is higher. Okay. And again, you also have a completion threshold, which is as soon as I come within 1 meter of my goal destination, then I'm going to assume that my goal is finished and I am there. It will finish the travel task and move on to the next task and essentially assume that that goal is complete. Okay, so the other goal-based force is an AStar, travel path force. So there are multiple different forces associated with the AStar travel path force. Again, like with the other goal-based force, when you have an AStar travel force, the agent system becomes a navigator for the object, such that it will notify whenever it gets a travel task, it'll notify the agent system. In this case, the agent system will communicate with the AStar network, and the AStar network will build a path for the agent. Then the agent system will set the first node, the first point in that path as its current target node. Okay, so at any given time when the agent has a goal, when it's traveling, it will have a current target node. Okay, and then it will apply forces based upon that current target node. The first one is it is attracted directly to the node. This is the node attract force. Again, you specify a scale factor and an exponent for the distance from the node. In this case, usually the exponent is going to be positive, meaning as I get farther away from my path, I probably get a little bit more antsy and I want to get back onto my path, right? And so the force increases as I get farther away from my path, okay? In this case, in the equation, n hat is the normalized vector directed to the agent's current AStar path node, or in other words, from the agent's center to the AStar node's location. And you have a distance from that node that you raise to a thing, to an exponent. You also have the path aligned force. This is generally, I want to go in the, yes, I want to go toward the path, my current point on my path, but I also generally just want to go in the direction that the path is going. So this is your path aligned force. So here you have a p hat, which is the normalized vector in the direction that the path is headed. Or in other words, the vector from the agent's last target AStar node to the agent's current AStar target, or target AStar node. So it essentially creates a vector that is going in the direction that the path is going. You know, in some cases, I want to get onto my path, but if there are a lot of other agents that are pushing me away from that path, then in general, I can still move along the path just by going in the same direction that the path is going. And so that's what this path aligned force does. You also have a goal force. Oh, I guess going back, you note that this exponent is likely going to be negative, which means as I get further away from my path, my inclination to go into the direction of the path, may decrease, so that
uh, you know, as I get further away from the path, I kind of want to just get more back onto the path. If I'm close to the path, then I want to go along the path. If I get further away, then yes, I want to go along the path, but I kind of want to more get toward the path, get back onto the path. You also have a goal force, which is the same as the other travel destination based goal force, which is once I get close to my final goal, I want to apply something that says I'm almost there. I want to now get directly to that goal. And so that will apply a force that's directly to the final goal. You also have a path progression angle. This is the thing that decides, okay, if I am traveling along my path, when should I update my current target node on that path? And what it says is uh, if my if the angle between my node attract force and my path align force becomes greater than some degree angle, then I should update my current target node to be the next node on the path. So in general, you kind of want to say, if I were to say 90 degrees here, then what that essentially means is I don't want my node attract force to fight against my path align force. They should be going in the same direction, generally, at least not more than 90 degrees separated from each other. If they are more than 90 degrees separated from each other, then I probably need to update my current node so that it's further along the path. Initially, we started out with 90, but over time we kind of thought over some experience of doing examples models, 120 degrees seemed to be a somewhat good estimate of when I should progress along my path. You also have a path recalculation timeout. In some cases, you want to go along your path, but if there's a lot of agents around you, you get pushed around. And sometimes you get pushed around behind walls such that your path node gets on the other side of the wall and you are behind the wall, so you're kind of pushing against the wall and you can't go anywhere, so they get stuck. So the path recalculation timeout says if I have not progressed on my path for more than 20 seconds, then I should completely recalculate my path and start over again. So this is a way for you to prevent people from getting stuck. There's also a completion threshold. Again, if you're within 2 meters of your final destination, go ahead and finish your travel task. You also have some checkboxes here. So this checkbox, add barriers as static agents. What this means is if I check that box, then my dividers and my barriers will actually be static agents. I talked about this earlier. They will be static agents that are recognizable in the bounding volume hierarchy, such that they are recognized as neighbors to other agents. And then you can apply forces to those agents. So if I want to be repulsed away from a wall, then you would check this box, and then repulsive forces, other repulsive forces would be applied to that divider. You can also enforce AStar node direction limits. This is essentially what it means is if I go into my AStar navigator and I show my grid nodes, let's see, I think I'm okay there. What this means is you have these node directions that are kind of enforced by your dividers and barriers. What it'll mean is if an agent is here, then it'll kind of do a hard limit, meaning I cannot go this way if I'm over here. I cannot go that way. So that's another way that you can kind of enforce the AStar, I guess, direction system or travel system. So that's the AStar travel path force. The other forces are a custom force, which is essentially I get to define the force myself through custom code. You can apply it per neighbor and then apply a maximum distance, or just a general custom force that's applied just to that agent. That's the custom force. And then you have a random force. The random force, you just define some magnitude, and it will apply a random force in a random direction for that guy. That's essentially create some randomness in your system. Okay, now for the general parameters of a social force behavior, you have the update interval, which is how often will this update all of the forces for my agents. You also have this checkbox, which is forces as speeds. What this means is the default, it will essentially apply forces to an object, and those will become like accelerations. So you apply a forces, and then he will accelerate in a certain direction. If you check this box, then instead of those forces being accelerations, the forces themselves will become the speeds of the objects. So when this box is checked, it goes through and calculates all of the forces, and then after it has calculated the force for a specific object, it then just makes that force, instead of being an acceleration on the object, it just hard sets the speed of that object, of the agent, to whatever the force, the sum of the forces was. So that's that checkbox. In saying that, I should also note, both with this and without it checked, the speeds are bounded by whatever the maximum speeds of the objects are. So in here, if I have an operator that is an agent and I have a max speed of 2, then when it calculates the forces, it will say, okay, if he's currently going 2 meters per second already, and then I apply a new force that makes him go more, it will actually bound it such that it will still accelerate or change its speed to go toward the forces where it's going, but it'll make sure that it only goes a certain speed, or it will bound it by that max speed. It will also bound the forces by the acceleration and deceleration. The way that it calculates that is if the force is going forward based upon its speed, then it'll use the acceleration as a maximum bounding point. And if the force of an agent is going against its speed, then it will use the deceleration as a bounding point for that object. If you specify accelerations and decelerations as 0, then it will just assume that it can apply, however many forces, but it'll still be bound based upon the max speed of the object. You also have a parameter on here, which is a threading model. So the default is single-threaded. We've added this mechanism, which is multi-threaded, which is kind of experimental. So when it does an update, it can actually update each of the agents concurrently. And so it can split that work up across multiple threads, which can potentially improve the speed of updates. So that's the basic general parameters for a social force behavior. Let me show you the parameters for a proximity detection behavior. They're very similar. You have an update interval, again, same as the social force behavior. You have a proximity radius for the behavior, which is I am detecting, I'm detecting entering and exiting proximity within this radius. And again, you have a threading model, either single-threaded or multi-threaded. You also have an active rules rule on the proximity behavior so that you can have certain proximity behaviors only apply based upon certain filters. And again, it could be self-based or neighbor-based. And again, as I mentioned before, you have an on-enter proximity, on-exit proximity, and on-in proximity. If I look at the general tab, or let's actually look at the agents tab. So if I right-click on this guy and add him to this social force system, if I click off and then click back on, you'll see him in there. On the agents tab, you can specify for each agent which behavior is activated at the start of the simulation. So I can say proximity behavior off,
social force behavior on, or whatever I decide to do. Based upon each of the behaviors, you can specify which agents have which behaviors activated. And finally, there is the general tab. I believe I've shown the show bounding volume hierarchy and the show agent state info options. There's also a checkbox that's on by default, which is resolve distances and forces on the XY plane only. So in this case, if it's checked, then it's going to look at a proximity radius that is essentially just bounded, just looking horizontally around the object. It's not going to be a sphere with a radius. It'll more be like a circle with a radius around that object. So that is the agent system. Hopefully this has helped you to kind of get an idea of what some of the capabilities that you can do with the agent system behavior, and hopefully we can get some feedback where feedback is welcome for feature additions or improvements, and obviously bug fixes if there are bugs found. But hopefully this can help you to simulate some of the social distancing things that may be prevalent now. So thank you.